Hello everyone, welcome to the EIDF Cluster tutorial. More specifically, today I'll be giving you a primer on the University of Edinburgh EIDF Cluster, including introductions to Kubernetes and Docker, as well as comparisons to Slurm when it comes to the cluster scheduling, and Conda and pip when it comes to Docker. Right, so let me just switch my slides. All right. Okay, so yeah, the agenda has quite a few items on it today, but we'll slowly go through them. I'm filming this on a rush, so it's just gonna be one take. So you might benefit from just increasing the speed a little when you're watching this, as I will be taking pauses here and there to collect my thoughts. Okay, so the agenda today starts off with introducing the EIDF Informatics community that we have built. This is mainly around a Slack group and a GitHub repo. Then we'll go over what Docker is and how it relates to Conda and pip. Then we'll have a short demonstrator of creating running a Docker container, as well as pushing it to a GitHub repo. Then we'll go on with introducing Kubernetes and how it relates to Slurm. We'll then go over what is basically available on the EIDF cluster in terms of hardware and the software abstraction layer that's available. And then we'll go full hands-on with just how we create an account for the EIDF cluster, how you apply for access, then how we go over the first login, which is a bit of a doozy, to be honest. So it might be a blocker for you. So step number 7, you will probably want to go over later on your own as well. And then we'll go over how one can basically run Kubernetes Jobs using the standard way, which is YAML manifests, and then I'll transition into why the various disadvantages of just using YAML inspired me to write Kubejobs, which is a Python wrapper around the Kubernetes YAMLs that makes things a lot easier for us, I believe. Then we go over some just overall good cluster etiquette that we should have. Then go over an honest and opinionated, I guess, overview of the current state of the cluster, both the good and the bad. I will then just sort of like mention the folder with markdowns that we have that basically showcase the current problems, and depending on whether you run into any of those, you'll know whether this is something that's already a problem and then people have been informed, versus whether it's something new that you should report, etc. And the final one is just how we submit tickets, which is a very, very useful thing to know to do when it comes to the EIDF cluster. Okay, so first things first, if there's one thing you're going to take away from this whole tutorial, it should really be that if you want to be able to use this cluster effectively and without running into each other's legs, you need to join the community that we've built. That exists in a Slack server and a GitHub repo. Links available here. I will be sending around the slides, so you should be able to just click as I'm going through this as well. Okay, so because I noticed that I needed a lot of links in the slides, I decided to just make a slide for links, because that means that you can just come back to this one whenever you need to click on something. Yeah, I'm just gonna really briefly go over what they are. Number 1 is the Slack server invitation link. Then it's Kubejobs. Then we have the GitHub, where we all sort of report issues and discuss problems. Then number 4 is essentially, it's part of that GitHub, but I wanted it to have a specific, like, on its own private link. It basically shows what the first community meet that we had came up with in terms of policies and how we voted on things. Then we have the official documentation. Then a GitHub repo that has lots of like Kubernetes workflow nuggets that I sort of had to develop for myself over time, and I hope it's useful to other people as well. Number 7 demonstrates how you can basically build an ML project that is stateless and fault tolerant. And what I mean by that is by using Hugging Face datasets and weights and biases, I was able to essentially build a minimal repo that allows you to launch jobs that when they die, they can basically pick up after themselves once you rerun the exact same command. And this is super useful when you're running on a cluster where your job might die at any moment, but then it will automatically be rerun. So if you have a stateless, fault-tolerant experiment suite, then you can go from there. Right. Then some links about how to build Docker images and how to push them onto a hub. Then we have the EIDF portal. Number 10 is going to be very, very important for all of the slides. That's the tutorial repo. It's where I have the code that will be running in this tutorial. And then I have a number of templates that show a more complex, realistic Docker files, framework workflows, and then finally the folder with the identified issues that the community has found, so you are aware of everything that's going on. Right, so starting off, these slides are targeting researchers and students that are already comfortable using Slurm. If you have not used Slurm, you should still be able to use the cluster after going through this talk, but many of the reference points I make with Slurm will not make sense to you. So when I do that, feel free to sort of watch that, but it may be less understandable. Right, so the overall aim is to basically help people understand and transition to the cluster, and also to introduce and demystify concepts like Docker and Kubernetes. And we'll be doing that by comparing them to Conda, pib, and Slurm that we already have used. Right, so what's Docker? Docker is a containerization system that can be more easily understood as when compared with VMs, right? So VMs are complete hardware and software virtualization, whereas with Docker, what you have is you only virtualize the software layer, but not the hardware layer. What that means is that you end up needing it's a lot more efficient in terms of resources. It's a lot smaller in terms of footprint on your hard drive and in your RAM, and the boot up is basically blazingly fast. So just a small comparison, if you are loading up a VM of like Ubuntu, maybe it could take like 10 to 50 seconds to start loading up. If it's the first time you are using it, it's gonna have to install Ubuntu and whatnot and all those things. Whereas with Docker, once you have built an image and then you run it as a container, it takes like half a second to get you into an Ubuntu system, for example. A few key things to note about Docker can be seen when we compare them with Conda and pib. So you all probably know pib is the Python package management system. It's Python only in terms of what it can offer. And then we have Conda, which is a virtual environment management system that can support installation of Python and non-Python packages. And that's great. Like for example, if you were using a Slurm cluster before, Conda was probably the thing you used, because oftentimes you had to install things beyond Python, and Conda was the only way to do it because you didn't have sudo access. Now, when it comes to Docker is essentially a layer even below Conda. So whenever you build a Docker image, what you essentially do is define a sequence of layers, each layer being a step that your system should follow. And usually those start off by defining an OS. So what that means is that maybe you're on Mac OS, you can build images that run on Ubuntu, Windows, Mac OS, different versions, and whatever else it is that you need, including like all sorts of interesting versions of Linux, for example. So in other words, not only does Docker allow you to define everything from the OS layer upwards, but it also provides you sudo access. So if you need to build your own CUDA kernels or install a package or a system, for example, a few years ago we had an issue with on Slurm, we had an issue with installing a particular brand of RL training environments because we didn't have sudo access, and we had to like jump through like hours and hours of hoops to find a way around that. But with Docker, you don't have to worry about that at all. You basically just, you start fresh, you choose an OS, you start adding things that you need, you have full sudo access, and you can basically do whatever it is that you want. And once you have built your image, it can then be run as a container on any platform, keeping the packages and the OS and everything else exactly the same. As you understand, this is great for reproducibility and compatibility in research. I'm sure that some of you have probably went down the rabbit hole of creating a beautiful Conda environment, making sure that your code is running perfectly, and then you have to run it on a new cluster or on a new machine, and suddenly some of the packages that you have are not compatible with that OS, so you have to find a different package version, but that actually breaks things, and you end up in a dependency hell. With Docker, that's no longer a problem. You can basically, you build the thing once and it runs everywhere. And I think that's like very good for everyone's time. Alright, so now we're just gonna transition into a tutorial style coding session. So I'm just gonna switch to my screen and bring up VS Code. Let me just make things a bit bigger. Hopefully everything is cleaner now. And what we have here is the actual tutorial repo that I have created. Now, let's start with a simple Docker. This is what I'm going to be doing right now. So as you can see here, you can consider this whole thing like a sub project, essentially. This is how a project would look like at the root. So I have a README file. Just give some steps that you can follow. I'm gonna be applying the exact same ones right now. Then we have a small Python file, literally just print something with reach. And then we have the Docker file, which is what builds the Docker image that we need to run our code. So essentially, there's a number of instructions within the Dockerfile style that allow you to do different things. So I'm gonna be passing around a cheat sheet later on, but for now, a few commands that we'll be using is from, you can consider it import. It's the same as import in Python, basically saying, okay, import Ubuntu, and that's that. You haven't just installed Ubuntu. And then we go ahead and we update it. We install Python 3 and pip, and then we install reach. Then we copy our hello world py file from here into our image, and then we run this command, which is essentially run this Python script, and this is all this image does. You can imagine that in a machine learning environment, this would be your experiment script, for example. In a more cloud computing environment, this could be your database service, for example, or something else that you want to start. Now, let's have a look at how this works. So I'm inside the project. Okay, that's correct. And then the first thing you want to do when you have a Docker file is first you have to build the Dockerfile one. So if you build this, it will generate a Docker image. And just to put things in perspective, a Docker file can be used to build a Docker image, and then a Docker image can be run on a machine using the Docker engine to create a container. So a container is basically Docker image plus a machine plus Docker engine. All right, so there's a number of commands for Docker. Obviously, you can Google most of these. Also, ChatGPT has a really good understanding of Docker. So if you ask it, it will probably know to help you as well. So for now, for today, essentially, we'll be going over build, run, push, and maybe login. So yeah, let's start. So I'm just gonna build my Docker file. All I have to do is build, give it the folder into which to use the Docker file. So I'm running symbol Docker right here. So it's gonna use this Docker file, the one we just looked at. Then you do touch T, it means tag this, give it a name essentially. And I'm gonna give it the name symbol Docker latest. So generally here you can have a specific like version or whatever else you want to have. All right, so building this up. That was it. I should also note that Docker allows for incremental builds. So what that means is that once I've built my Docker container once, which I have done this before even coming to this tutorial, as you can see, it just rebuilt the whole thing in like a couple of seconds. Last time I ran this, it took like maybe a minute or so. So the other thing about the incremental build is that if, for example, I add a new command towards the end, let's do it that way, for example, it will only have to run the new bits, and the way that the incremental build picks up changes is it follows a sequence of things. If something changed, it assumes something has been forked, and so it has to rerun everything after that. So if I were to put this new command up here, it will need to rerun everything from here down. So the things that you change often, like your Python project, etc., you want to have at the very bottom. So I'm just going to run this so you can see how it works. It seems to have failed to do what I wanted it to do because it couldn't find the file. And this is the kind of way that you debug this sort of thing. So essentially it's saying, oh, I couldn't find the file because when I copied it, it wasn't copied properly. So just redo that. And it seems to be failing again. So this is the kind of process that you should be expecting when you're trying to debug things. Now, let me just have a quick look. What I'll do instead of this is I'm gonna create an app directory, and I'm gonna copy this guy into it. This should make things a bit more likely to work. Oh wait. Oh, I see. So that worked. It's just that I had to change it there as well. Okay. Right, so it's still failing there. Okay, this is weird. So I have modified that line. Oh, yeah, sorry, I forgot about this guy. Okay, that was it. Right, so it's gonna build now, done. Okay, and now I can go ahead and run this. So the way you run images is just run. There's a number of extra things you can add that I will go over afterwards, including adding volumes, defining how much shared memory you want to have, mapping local volumes to remote ones, etc. So we'll go over that later, but just to keep it in mind, like there's lots of cool things you can do with run. So let's just go over there. Simple Docker. That should do it, I think. There we go. Printed hello world. Yeah, and then it exited. However, you can also do something like, if you want your image to be more general purpose, so for development, for example, if you just do like bin bash like this for your entry point, and then you do interactive, then one moment. Oh wait, so I haven't actually rebuilt this thing. So what I should do is rebuild this, okay, and now run it. There we go. And now I'm actually inside the actual container. So we always start from root. It doesn't pick up any GPUs, even though I have them, because I didn't install any drivers. I just installed the default Ubuntu. I will show you later how to ensure that it picks up the GPUs and everything. Yeah, so that's that for the initial tutorial. So let's move on to the slides again. All right, cool. Okay, so we've built this, we've run it, and now I'm just going to go over the process for how you can set this up to work with GitHub. So if we go back to our links page and click here, you get the cheat sheet I have for how to publish things to the GitHub Docker Hub. So long story short, you need to go and create a token inside your GitHub that has some specific instructions that Docker requires. So you can just do that by following this link and defining the correct permissions. So the actual permissions that you need are all of the permissions related to packages, according to this. But just to keep everything for completeness, let me just check here. If you just do push to GHCR, it should basically give you a page like this one. And then, yes, as I said, you need a GitHub token, and it has to have this scope. So that's that. And then you just need to follow these instructions here. Once you've built your thing and you have tested that it runs, you just export your key, your token. You log in with your username. Then you have to tag your Docker with this structure here, and then push. So this is how pushing works. I'm not gonna be doing it live, but you can try it at your own time and come with questions on the Slack if you have any. Now, I'm just gonna be going over Kubernetes and how it relates to Slurm. First, I'm gonna start from Slurm. So what's good and what's bad in Slurm when it comes to machine learning research? So it's very efficient at managing like static, long-running jobs. It's quite simple to use, and transitioning from like Linux to Slurm is fairly intuitive. And it's pretty good at like batch processing, where you have a number of things you want to run. Some things have to be run concurrently, some other things can be run later. There's a scheduler, etc. The problems are that the environments have to be pre-configured on the head node file system and given to batch scripts. This is not great because the head node has limited resources to sort of set things up. You have to interact with file systems. It's quite slow. There are lots of problems with that, and it's just lots of very, very time wasting. Furthermore, Slurm doesn't automatically scale when it comes to on-demand resource provisioning. So yeah, if you want to scale something up more, it's harder to do compared to Kubernetes, for example. And there's no built-in support for containerized environments. So when you're trying to manage your software reproducibility, compatibility, consistency, it's a lot harder. And there's overall lower synergy with tooling that's available for cloud native tools. And the last thing I would say is that with Slurm, you have to use Conda, and you never have sudo access. So if you want to have a very specialized container, like a very specialized environment, then that's gonna be a problem for you. Now Kubernetes again, right? So the positives are that it offers containerization out of the box. You can do dynamic scalability within it. There's a ton of open source tools with it in order to play with machine learning and AI. And in deep learning, most of the time, we, other than the dataset and the models that we can actually just receive from the internet in most cases, there's no other state that we have to keep around, like the types that you would find in a large software infrastructure. So this is great for Kubernetes that is well suited for this kinds of stateless tasks. The cons is that there's a steeper learning curve because you have to learn Docker, then you have to learn like how to build jobs for Kubernetes, how to run them, how to sort of manage things. So yeah, it's a bigger challenge for students when they're first starting on this. However, it's one of the most valuable skills on a CV you can have when it comes to like jobs in the market right now. So if you're doing ML and you can also do Kubernetes, your value just went up by quite a bit. So Docker, Kubernetes, ML, these three things generally coexist right now out there. So and when you have a very long running task, Kubernetes is basically not able to efficiently manage resources around that, because once somebody gets the resources, Kubernetes generally won't try to kill that, which is something that Slurm also had as a disadvantage, to be honest. Right, so just gonna go over the cluster that we have and what it can offer to us. So there's basically a ton of GPUs. The bottom line, it says 70 here. It's outdated. It's actually 88, 840 gigabytes. There's 32, 880 gigabytes, and there's the other MIG types here that are basically, you grab a full GPU, you split it into like two, and you get the MIG here that has 20 gigabytes. If you split it into 8 pieces, you get the 5 gigabyte versions, and so on and so forth. There's a ton of RAM on these machines. We're talking half a terabyte. Well, actually, I think the per node maximum is 890 gigabytes, so it's quite a lot. There's petabytes worth of hard drives that you can create and connect to your instances. And yeah, generally the infrastructure, the actual networking, and all of those things are extremely fast. So when it comes to the hardware, the way that the infrastructure was put together, all of everything below the Kubernetes layer has been done extraordinarily well. So I think that's gonna leave this one here. There's a lot of additional resources, as you can see here in the documentation. Feel free to go through that. Now, I'm just gonna be going through a process that may block many of you. So essentially, if you go on this GitHub, you have every step you need from getting started to even running jobs, etc. So what I'm gonna do now is I'm just gonna go to the EIDF portal, and I'm gonna show you the process for submitting an application to get access to EIDF. So what's going on? EIDF. There we go. Okay, so if you point your browser to this website, and then you click EIDF portal, and you wait. One moment, what's going on? I think my browser is being weird. Sorry about that. Okay, so it's not my internet. I wonder if I need to be connected to the VPN. I think I am. Yeah, okay. So let me just try this again. Okay, just gonna click this down. Portal EIDF. Okay, that worked. Okay, so if it's your first time coming to this website and you're trying to sort of get access to EIDF, you want to click here. You want to click New Application. Let me just see. Yeah, you want to essentially, let me just see if there's a specific guideline for the name of your application. I don't think there is, but let me just confirm this because there could be. All right, so great. Also note that in order to access this, you need to have a safe account. I have a safe account, so it was signed in from the get-go. Okay, so return to the EIDF portal. Okay. Okay. Right. So again, I'm just gonna go back here. Let me just see projects. Okay, you should just go projects. I think this is a faster way to do it. So projects, request access. You choose the K80s support. So EIDF 029. Apply for that. I've already applied before, so there's no point here. I'm just doing it for the tutorial. Once they get back to you and you know that you have access, it should show up in your projects. So again, this is the home page. Click your projects, click here, and then click here. So once you're here in your first login, it should look very similar to mine, except there's not gonna be a key here. I'm gonna remove the key. So I'm starting from scratch like you are, and I'm also gonna reset my password. So I'm gonna have the same experience as you will. Okay, so let's go back to it. Cool, so I have a new password. This is the password. Just gonna copy it, even though copy paste doesn't work that well with the VDI login, but let's go. So click here. I'm just going to put these two guys next to each other. Tile them. Yes. Okay, so they're tiled now. So I have to log in. I need to put my username, which is over there. Okay, and then go ahead and in order to paste here on a MacBook, you have to do Control left click. I'm not sure what is happening, how this works on other platforms. I think on Ubuntu is right click, but that's as far as I understand. Okay, now I just need to retype the password. Unfortunately, I don't know of a way to copy paste here, so I'm just gonna have to type it. Bear with me, or you could just type in yours as well. It's gonna take a moment. Okay, I think I wrote it correctly. Let's find out. Cool. And now you have to add a new password, something that you will be using yourself. There we go. That worked. And now I can happily log out. So this goes away, and I'm left with the default thing here. We have a new password. So next step should be, let me just go back to my screen. Okay. And now it's gonna open up a terminal. So what you want to do is create an SSH key, like so. So I'm just gonna wrong server. Okay, so this is my local machine. What you want to do is SSH keygen. The rest is not necessary here, really. I'm just adding it. I'm just making the encryption a bit stronger. There's no reason for you to do that, but there's also no reason not to do it. It's very fast, so just go with this. It will ask you where you want to save this. I'm just gonna save it. Just gonna save it here for now. I'm just gonna call it users in that folder over there, SSH, and then let's call it EIDF key. Okay. It already exists because I have one, but I'm gonna override it. We have to provide a passphrase. Provide a passphrase. Don't forget about this one. And again, there we go. And so now we should have a public key as well as a private key here. What you have to do next is have a look at your public key. You will need to copy it and then come over here, press plus on the credentials, add your key, upload credential. Then, as you can see here, it's pending for approval. It will take a few seconds. Now it's active. And now I can go and happily install this key, like so. All right, and now, if I've done everything correctly, I should be able to use this command to SSH into the EIDF cluster headland. There we go. That did not work, and that's very nice. Let's see. So I did use the right public key, but that didn't work. Okay, let's have another look. Okay, I think it wanted a moment to propagate. Okay, that worked. Okay, so welcome to the EIDF cluster. So this is my home directory. You will have yours as well. And we're now in the actual cluster. So welcome. We'll be doing a few more things in this context, but let me just get back to the slides for now. All right. So there we go. Okay, so we've done this. Let's move on to the next one. So Kubernetes. So Kubernetes jobs are defined in YAML files. And a YAML file looks like the one you can just see on the screen right now. The schema itself is fairly straightforward, but also kind of annoying sometimes. As you can see, there's a template spec situation there. So you can easily get lost if you're not copy pasting and just changing things directly. So in this example here, you can see that I'm basically saying use the PyTorch image. I'm gonna call the container PyTorch, and I'm gonna be running Python and then script.py within the scripts folder. I have a number of mounts, volume mounts. This is the kind of thing that allows you to have a hard drive that's external to your instance, and what that means is that once your pod or once your job completes, you will still have access to the data. So this can be very useful if you have a data set you download on the volume. We call these PVCs on the context of Kubernetes, or in other words, persistent volume claims. And then you download your data set, or you save your results on it, and it's going to be accessible to you and other pods and jobs in the future. Most of these are straightforward. There's something called bug of limit 4 here. It means that this job will run until it fails 4 times, or it succeeds 1 time, essentially. All right, so now I'm just going to sort of demo this sort of thing, and let's just start. Okay, we have this Python script, which is just here to help us demonstrate things. There's run experiment function, takes a seed, generates random matrices, computes the matrix multiplication of the two, and prints out the result. This fire package here is basically a very convenient way of adding arguments to things that can be run from a command line. Basically, it grabs everything in here, creates an argument for it, you know, which is pretty convenient. Again, just gonna show you how the running situation works. So I build the Docker file. And then I run it. So there's a number of arguments here that we should definitely go over. So volumes allow you to mount a host OS directory to the container. So left hand side is the local path, right hand side is going to be the container path. So the path within the container that's going to have the things. Then you have the shared memory size. I would recommend just use basically the full RAM that you have, because if you're using PyTorch or TensorFlow or JAX, most of those make use of shared memory to make things very efficient. Without this, you will have very slow data loading or even just errors. Like PyTorch in particular will error out. And then I just have the name of the image. As you can see here, I have ghcr.io. That's the GitHub, Docker Hub domain name. And then every one of us that has a GitHub account can basically host their own Docker images under their name. So I'm just gonna run this. There you go. If you go in the dev code folder, you can see that I have access to all of my code. If I wanted to development, for example, but just for making sure that the main code works, I'm gonna activate my environment and then just run this command up, and then simple ML, and then run.py. And then it failed because I didn't pass a seed, which is nice. So I'm just gonna tell it now to use this, and there you go. So it printed out the results of that operation. We know this works. It's almost pushed. Once it's pushed, I'm gonna be able to demonstrate to you the Kubernetes cluster in action, hopefully. It's possible that we won't be able to get a machine, but at least I'm gonna show you how you run a job. Okay, so let's go back to this. Now, what I'm gonna do now is continue with the rest of the slides that don't require me to do demos on Kubernetes, and then come back for the final two demonstrations. Right, so this is part of the demonstration. Okay, so basically, we're currently in a situation where there's basically so the EPCC is spread thin when it comes to their operations. So we need to be really mindful of each other when we use the cluster, and be kind to each other, basically. Making sure that we are mindful of other people and their work, and that we're not, hogging resources too much, or doing something that may cause other people a problem. Right now, the cluster does not have per user permissions. What that means is that you can't kill other people's jobs, and you may do that by mistake. But try not to do that. And if you do, please contact the people, or at least post on Slack that you have done that, and show the jobs that you killed by mistake, so people can go in and fix the problem. The other big problem is number one here. People tend to hog machines using the while true sleep as their, let's say, the command they use within their container, which what that means is basically you have an infinite loop running, and so your pod is not really trying to run a particular experiment. It now becomes your own personal development machine or development server, and that means that you're making less efficient use of resources, and it also means that you might forget about that, and then end up wasting lots of compute time that other people could be using. And it's also harder for others to predict when your jobs will finish and all those things. So I would recommend that when you're running jobs, you spread them out into as small pieces as possible, such that you may have 10 2-hour bits, for example, for a 20-hour job. That would be ideal. Obviously, I know people are probably not going to do that, but basically the smaller the jobs that you are submitting, so if you have a high number of jobs but they're small, that's fine, because those finish quickly in general. And between like jobs being submitted, people have the ability to at least get in line in the queue and get access to something in good time. Right. Whenever you have a question about whether if you need more GPUs and you don't have them, or if you're observing something weird that somebody is doing, or you have like a question about how you should be doing something so you don't cause other people problems, just come to the Slack, ask away, and we'll figure it out as a group. 4 is what I said earlier. Small pods that execute quickly are generally like the best thing ever when it comes to like these kinds of systems. 5 is optional, but I think it's gonna make your life way easier when you use Kubernetes or other things. Like any cluster or server will be happy with this one. So if you can ensure that your jobs are stateless and fault tolerant, and can continue when you just rerun the same command, then Kubernetes will play really well with it. You are not gonna worry whenever a pod dies. It's just gonna restart. You won't even know it died. You'll come back and your job will be completed. Or if it's not, you will be able to very quickly get back on track. Remember to report issues on the Slack and via tickets to EIDF. Generally what we do is people report on Slack, and then we can generally figure out whether this warrants a ticket or it's something that we can deal with internally. 7th point, be good to each other. And just like I want to at this point here just go over the state of the cluster. So the hardware, the infrastructure, everything done at those layers is incredibly useful. It has allowed me to do work that would have been impossible without it. I'm very, very grateful for having so much disk space, so many GPUs. I think once we iron out some of the current problems, it's going to be a great resource. With that being said, there's currently a number of problems, mainly due to how the EPCC tends to schedule their development jobs, I guess. I'm not entirely sure, but like that's what I've picked up from conversations with people, and that leads to a lot of weirdness. The latest weirdness that you will come to realize soon is that last week Informatics was cut off from 120 GPUs down to 60 GPUs because the university-wide version of the cluster would be opening up, and they wanted to make sure that GPUs were available for the other schools as well. That caused a lot of problems because it was unexpected, and also because the 60 GPUs that we are not using are not being used by anyone else, and so that creates a bit of a weird situation. But anyhow, so you'll probably catch up with those when you join the Slack group. I want to point you to number 1 here, which is the previous voting and policy discussion we had in the first, essentially, community meetup that we did. And the second one here is a folder that has all of the known problems that we want APCC to fix. Finally, I have built a template for tickets so that we're on the same page whenever we report things. Also, this is how you submit a ticket. You send an email to this address. That's it. That's how you submit tickets. But to make things a bit more consistent, I would recommend you use this template. Many of these you will not have to include. I'm just saying that this is ideally what you want to have. And that's that. So I think for any questions, just contact me on my email or just add Andreas Antonio on the EIDF Slack group. And now let's just finish this off by going through the last two demonstrators. Okay, so it should have, yeah, it has been pushed. Now I'm just gonna push it again. So it pushes the latest changes that we made earlier. You will notice that the push is also incremental in the sense that it only pushes the latest bit and it doesn't have to repush everything else. So this should, yeah, this should make sure that like the push is quite fast. Let's have a look. It's pushing just one layer. There's a number of layers that are not there yet. Okay, it's done. Perfect. Okay, so now let's go back to the cluster. So this is the cluster. Okay, let me just go to launch job. All right, so I will be coming to this later in a moment, essentially. But for now, I'm just gonna make sure that the YAML I use is a sensible one. So command bin bash, the arguments are Python, etc. I'm gonna be using an 140 gigabytes. Okay, fair enough. This is good. I'm gonna run this again, get the results, and run it as a job. So you won't have to do what I'm doing right now later. I'm just gonna explain why I built the Python package that allows you to run everything faster. So just to give you an overview of what's going on here. Okay, so this is the cluster over here. The command that you will be using most of the time to do everything that you do is going to be kubectl. So this is the command that allows you to do anything on the cluster. It's similar to Slurm's like commands that exist, like Slurm had like sq, srun, etc. Kubernetes has everything under kubectl. So if you do help on it, it will show you all sorts of things that you can do. Kubectl also includes a autocomplete, an autocomplete script. So if you just do kubectl completion, your terminal type. So I'm using like fish, and then I search that. Now I have autocomplete, which is quite useful. But anyhow, let's just proceed. So in order to see what jobs people are running, just do that, and you can immediately see a number of different like jobs here, their completion status, how long they've been there, etc. If you want specific details on a job, you can do describe job, and then maybe you just choose a random one. Let's choose job test or something, and it shows you what this job was about. It seems to have been exactly what it says on the name, just the test job. It doesn't have almost anything in it. Let's just try another one that has a bit more interesting things. Let's do the llama fine tune. Okay, so this person is doing things right, actually. They even have their keys properly hidden. You can ask on Slack how you can do that, but anyhow, so this person is basically so they're just running. This is the command they use. They are cloning this directly. I would not recommend this. I would recommend that you build your Docker image with the exact Python files you need, and whenever you have new pieces of code in it, you just do git build, you just do docker build, docker push again, and it should take a few seconds, similar to how it would be for git add, commit, and git push, right? So just to like clarify that a bit more, what I'm trying to get to here is that this on this script here, it seems that this person wants to be cloning their repo every time. That's fine to do, but it's gonna add a lot of extra, maybe gigabytes worth of extra stuff, because it's gonna have to include the whole .git directory. And instead of doing this, in order to ensure you have even more compatibility and reproducibility, you can just, every time that you need it, you can just do, let's say I have a folder. Let's go back to this guy. So let's say I have this folder here. No, not this one. Wait. Yeah. So let's say you have this folder, and I made a change, right? Let's say I'm in this ML Docker here. I'm gonna like change my code. The code is going to be printing. It's gonna be printing. Let's see. Shape of C, and also the mean of C, and a number of other statistics for C. Let's do it this way. Okay, perfect. So let's modify this, right? You kind of imagine this is something that you would do git commit for, and then on the other end it would git clone. But I don't recommend that, because one, it adds a lot more layers in your image, a lot more space, and it also makes it a bit harder for you to track different versions as they keep evolving. Whereas if you do, it's already, yeah, if I just do git build again, and I provide, let's say the previous version was 0.1, let's say this is 0.2, for example. It's just gonna build this super fast, and then I can just docker push again, super fast. And now, you know, it's gonna be up there. I can just use this one, and because I'm using different version numbers, I also know that I'm using exactly this one, for example. Yeah, so let's go back to this guy over here. So yeah, he's running this command. This is how he runs his job, her job, I'm not sure. It's using 24 CPUs with 111 gigabytes of memory. You might wonder why this number. It's because it's exactly 1/8 of 190, which is how much there is in a given node. And if you're gonna have 8 GPUs in a node, you want to have exactly 1/8 of the resources if everybody's gonna be using equal amounts. Right, cool. So these are the jobs. And now let's go back to our YAML file. So this YAML file here should basically create a job that will create pods that have this name. We will be using, let's find the container name. Okay, the image here, let's do this one, which we just updated. We're gonna be using these kinds of resources, and we're gonna be using, so the shared memory is gonna be the whole thing that we have access to, and we're gonna be using this GPU, etc. So how do we actually run this thing? We just do kubectl apply f, and then we just go into simple. Wait, I'm in the wrong folder. Let's go to the correct one. Okay, so if I do kubectl apply f, and then do simple YAML Kubernetes, and then simple YAML, and we also have to say validate false. This is just a weird intricacy of the cluster that we have here. In order to see the commands I'm using, they're here. So in the README file of every one of these folders, you can see the commands that I'm running. So you can do it on your own time. Okay, so it says that the job has been created. So let's have a look. Get jobs. Tutorial note. This is our job. It's been running for 7 seconds. We can see details of the job like so. Okay, and then we can see why it's not running, which is this means that Informatics has touched the 60 GPU quota, so it's not gonna be running. That's fine. So as you can see, YAML files, you know, they're nice, but they don't allow logic to happen, and generally speaking, within a, let me just go back here. Yeah. So within a machine learning research environment, we'll have hundreds of jobs. So this means hundreds of YAMLs, and basically you need a way to automate the YAML creation, and a way to ensure that you can add logic, so you can basically modify things as you need. And so while you can write a script that automates the YAML creation, what would be even better is to have a Python package that has a class that defines all of the key fields and automatically creates YAMLs and automatically runs them. So it abstracts away all the YAML stuff and all of the kubectl apply and whatnot. And all you have to do is just create the Python class and run it. And that's why we created Kubejobs, which is a minimal Python package that allows us to do what we need to do here. Like, instead of create YAML and doing whatnot and whatever, all we have to do is import job here, give it a name, pass an image and the command, and then run. And that's it. That's everything. If you want to see the YAML and rather you run it yourself, you can just generate it that way. Now, I'm just gonna go back to the situation over here because I want to touch on another thing before I go for Kubejobs. So there's this thing that we call PVCs. Those are persistent volume claims, and they're how you will be storing things in a non-volatile way, such that when a pod or job finishes, you still have access to the data. So if you do kubectl get PVC, you can see like here all the PVCs that people have created. You can see the size of the PVCs, like 1 terabyte here, 2 gigabytes there, 5 terabytes there, etc. And when you run a job, you can actually connect the PVC to your job using the volume tag, like here. So if you just do name, you give it a name, and then you say persistent volume claim, this is the name of the claim, and then you need to also add it as an actual volume mount over here. And then basically when this container is created under /data, you will have all the data that's within the PVC, or if it's empty, you'll be able to like store stuff there. Now, finally, let's have a look at Kubejobs. So Kubejobs abstracts everything away, as we said earlier. You can see all it's doing in here. If you just go in there, it will tell you the kind of available GPUs there are. It will automatically add user information within your job, so you know and we know like who's running what. It has all of the arguments, all of the kind of functionality that you might need. There might be something more, but these are the things that most people should need. Number of CPUs, the RAM, how much storage you want, GPU type, GPU product, all of these things here. Even it has like how much deadline you want before your job dies. And this is great to have. Most people don't use this, but it's great to have because people know beforehand how long your work will take. But now, just to go back to things, this script here, what it does is it creates a PVC called tutorial PVC where we'll presumably store stuff for the tutorial. It's gonna have a read-write once mode, which means that it can only be connected to one pod at a time, and it can read-write on that. And then I create my job like so. I pass all of the key details. Then I can call generate YAML if I want to see the YAML, and then I can do job run, and it's gonna run the job. Like under the hood, you can actually see what it's actually trying to do. It's creating a YAML. So it's basically creating the YAML here, writing it on disk, running kubectl apply f. Everything we just did is just automating it behind the scenes. And it returns the error code if there's like a problem, and if there's not, you get 0, so you know things are fine. Is it 0 or 1? I don't remember. Anyway, so it returns whatever the everything is fine code here, etc. So if we go back if I run this script now, it should generate another job for us. Should generate a new PVC. Let's call it PVC1 because I think the other one is already exists. I'm gonna change the name here so it can be picked up automatically. Let's do that. So Kubejobs launch job. Okay, so it has run, and let's have a look. There we go. It's over here running. There we go. So with this, I think I'm gonna end the tutorial. I hope you learned useful things today, and feel free to come and find me on Slack so we can talk about this more. Have a nice day, and thank you for your time.